This is Schweitzer, and quick video on mathematical composition of liquids. So the math side of solubility. All right, so here we go. Again, this is 4-2C. So it's liquid. This is the states of matter, liquids, and the calculations. This is version C. All right. So, well, first of all, whenever we have a solubility situation, we have essentially a certain amount of solvent and stuff dissolved in it. There are lots of ways in which we can measure the ratio between these two items, the solute versus the solvent. And I don't know that one's any better than the other one. It just matter sometimes which one came up first and which one just stuck. Okay, so for example, we could do percent by mass. So percent by mass would just be the mass of the solute divided by the mass of the solvent, and this would be times 100, and there you go. We also could, rather than mass, we could do the volume. This is something that is very common for liquids in the food industry, mostly because it's easy to measure. I mean, if you're doing a juice, you can do 10% by volume very easily in a factory as you're packaging up juice boxes and whatnot. No need to weigh it, they just use a volume. All right, so otherwise, we're looking to measure the ratio of moles of solute to liters of solvent. This is something that is called molarity, and clear this quickly. All right, so anyways, so this is a relationship. So if there, for example, we have something that's 2, capital M means this is 2 moles per liter. Now this is a fictional example of a per 1 liter. This is 2 moles in 1 liter. And again, it's just a relationship. It's a linear ratio. So we could do a linear portion, 2 moles per 1 liter. Okay, how many moles would I have if I have, I don't know, 10 liters? Well, cross multiply divide, the answer is 5. It's just proportion. So we always want to be thinking of things in terms of proportions. How much would 1 liter have? How much would half a liter have? Half a liter here would only contain 1 mole. Okay. All right, so let's move to our couple of examples here. All right, first of all, 58 grams of NaCl is dissolved in 0.1 liters. Write the dissolving equation. What's the concentration of sodium chloride? What's the concentration of chloride ions? Okay, so the dissolving equation is going to be NaCl goes to Na plus Cl minus. All right. What's the concentration of the NaCl? So we're looking for molarity equals moles per liter. Okay, so I'm looking for this. So I got to find these two things. So the volume is 0.1 liters. 0.1 liters. Okay, and now I got to find my moles. Well, I don't have the moles. It's not provided for me, but I do have the mass, and I have the formula, which allows me to flip. The formula allows me to flip from grams to moles. So let's do that first here. So to flip, this, how many moles is 58 grams? Well, I don't really know that, but I do know how much 1 mole is. So here comes the proportion. So NaCl, this is going to be approximating about 23. This is approximating at about 35. So that's AMUs per atom or grams per mole, giving us a grand total of 58 grams per mole. Now I'm estimating there. Okay, so that means I have 1 mole. That's how much 1 mole weighs. Okay, so that number sets up nicely. So I have 1 mole in 0.1 liters. So if I portionalize that to 1 liter of volume, I'd have 10 moles. So my answer is going to be 10 moles per 1 liter. What's the concentration of the chloride ion? This is something that's important to see, that if for every one of these guys, I get one of these. So the answer of this guy is also 10. You could look at it as you have 1 mole of NaCl, and you're going to get for every 1 NaCl, you get 1 Cl. So you still have 1 mole of Cl's ions divided by the 0.1 liters gives you back your 10. Drawing a picture of this. Okay, well, what will it look like? Well, it'll be Na plus Cl minus. You could possibly show a size ratio here as well. But other than that, however many you add just is proportional to the concentration. All right, next one. 47.1 grams of magnesium chloride dissolved in 0.1 liters of water. So this is the exact same problem. Let's write out our dissolving equation. Magnesium chloride produces magnesium 2 plus ions and 2 Cl negative ions. All right, so we want to figure out the dissolving equation. Done. What is the concentration of the magnesium chloride? We need to find out the moles per liter. So this would be 0.1 liters. Add the molar mass of this thing up and solve for the moles and plug them in there. So I'm not going to do all the math on this thing. You do the same exact way. Well, let's just do this one quickly. We didn't have to add up and do much. So first of all, the molar mass of magnesium. Let's look magnesium up. Magnesium is 24.3. Okay, so 24.3. Chlorine is estimating at 35.4, and there's 2 of them. That's 70.8. Add that together, 70.8 plus 24 equals 94.8. All right, so in this case, 94.8 grams per 1 mole. All right, so 1 mole weighs that much. I don't have that much. I got 47.1. So here we go. We'll do 47.1 grams, dot line, get rid of grams, go to moles. 1 mole weighs 94.8. All right, and it's a good chance I picked this number to be a nice fraction. 47.1 divided by 94.8, and I get pretty close to a half. Okay, 0.4968. So I'm just going to call this about 0.5 moles. Okay, for sake of numbers. Plug that into here. I'm going to erase this for a second. All right, thank you. All right, we'll put the 0.5 in here. 0.5. All right, that's magnesium chlorides. Divide out, and we get a molarity equaling 5 moles per liter. All right, so let's draw a picture of this thing. So if we dissolve it, we would get 1 magnesium and 2 chlorines. Mg2 plus. Make sure you show your charges on these guys. Cl minus and Cl minus. All right, so for every 1 unit we add, we get 1 magnesium and 2 chlorines. So my concentration of my chloride ion will be twice that of the whole unit. So 0.5 moles of this is magnesium chloride. So for every 1 of those, we get 2 Cl's. So I have 1 mole of Cl negative. And again, that's like saying I have 1 of these, I get 2 chlorines. If I have 10 of them, I get 20 chlorines. 1,000, I get 2,000 chlorines. If I have 2 moles, I get 4 moles of chlorines. So I'm doubling my number of chlorides. So so just 1 mole divided by 0.1 liters equals 10 moles per liter. And that's my answer for letter C, for the last one. All right. I'm not going to do all of these, I guess, here. The first one, we'll just kind of walk through how to do these. So how many grams of Na2SO4 is required to make 0.34 liters of this concentration? All right, so let's just talk about how to do this. Molarity equals moles per liter. The volume is, let's just mimic this over here. All right, the volume is 0.350 liters. The concentration is 0.5. You can solve for your moles. That's half of that, so what was that, 1725, something like that. And then flip this from moles to grams using the molecular weight of that substance. All right, so that's going to tell us how many moles we need, and the formula weight or the molecular weight will tell us how much 1 mole weighs, and then just use factor label and proportions to figure that out. All right, and it's going to be less than 1. A little more than a tenth, actually. So, either way, next one. How many milliliters of 3 molar H2SO4 are required to make a 450 milliliter solution of 0.1 molar H2SO4? All right, so in this case, there are two ways to make a solution. And let's take a moment and just kind of highlight that for a second here. So there are 2 ways in which a person can physically make a solution, and this is going to be some of the calculations that we'll use kind of surround around this idea. One of them is going to be literally, and this would be in water, so adding a solid, a solid, okay, to a solvent like water. And then the other one would be that just literally adding a liquid. Adding, okay, a liquid to a solvent. So in this case, another name for this second one, we just kind of did that first one, where we could solve that first problem was just the same thing. Dilution. Okay, so this adding a solid to some solvent is the exact same thing we just did in this problem right here. How much mass of solid required to mix to make this solution? So we use the molarity formula. We have a volume, we have a concentration, and we have to solve for the mass we need. This guy is looking at a liquid. So let's talk about this a little bit here. And that next worksheet we'll do some more of that. Anyways, so in this case, if I want to do a dilution, I'm literally going to add have a concentrated liquid, and I'm just going to add solvent to it. So let's say I have this much, and it's just got 3, 4, 5, 6, 7, 8, 9, 10. 10 units of things in this solution. And I'm going to simply dilute it. Now when I dilute it, I'm adding more solvent to this thing. So I can't dilute to a higher concentration. I just can add more solvent, and I can move to a lower concentration. Okay, so here's my new beaker after I've added this stuff. Okay, and now I have more solvent, but there's still the same 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And you should know that this got a bigger area, so it's less concentrated. So this is following the formula molarity equals moles per liter, and we're solved for moles, so molarity times liters equals moles. And you should be aware that if I double my molarity of a given volume, my moles doubles. If I double my volume of a given molarity, my moles double. So it's all linear proportions. So in this situation here, my new substance, my new solution, has the same number of moles. They haven't changed. So these are identical. But it does have a correlating molarity and a correlating volume. And with this formula, canceling out the moles, we get this formula. M1V1 equals M2V2. This is not your typical linear relationship. A linear relationship will go x1 over y1 equals x2 over y2. Many things we do in our everyday life follow linear proportion. Make $10 per 1 hour. Okay, or 2 hours, you make how much money? 10 hours, you make how much money? If you want to make $158.25, how much time do you have to work? You're just solving out, this is factor label. This is a reciprocal proportion. As one goes up, the other one goes down in order to maintain the balance. So, if these two are established, then if this is going to go down, then the concentration has to go up and vice versa. They don't move the same way. They're reciprocals. So, anyways, let's see how this works. I'm going to show this shortcut way here. All right, so it's saying here that this is initial concentration, initial volume, ending concentration, ending volume. Only thing I would mention here, your units can be whatever you want as long as you're consistent. And V2 equals V1 plus what you add. Okay, so let's go back to that next problem and see if we can use this on this problem. All right, so how many milliliters of this? This is my high concentration. So they want to know the volume of this stuff is required to make this volume of this stuff. So notice we're going from a high concentration to a low concentration. All right, so I just like to write this out. M1V1 equals M2V2. M1 is 3. Unknown value is V1. Ending volume 0.1. And ending volume is going to be saying make this total amount. So it's going to be 450. Okay. You very often can see the relationship between the number of times the volume is getting, the concentration is getting smaller, and the number of times that the volume is getting bigger, or vice versa. So, for example, right now, 3 divided by 0.1, my concentration is getting 30 times smaller. 30 times smaller. So my volume should be getting 30 times bigger. Now 30 is not as easy to see as other proportions, but if my concentration gets cut in half, my volume will double. So that proportion should be there to see all the time. So the actual math here, 450 times 0.1 is 45, divided by 3 is 15. So VI equals 15 milliliters. VI equals 15 milliliters. And of course, if you take 450 and divide it by 15, you're going to get 30, because my volume increased 30 times. So this is actually V1. If you want to know how much you have to add, like actual solvent added, it would be 435. Take this minus your total gives you what you're going to add. How much water needs to be added to a 12 molar NaOH if one is making this concentration of that. Okay, so let's do this. M1V1 equals M2V2. M1 is 12. V1 is, well, I don't know V1. Okay, keep going. M2 is 3. And ending volume, it's indicating here is 500 milliliters. 500. Okay, so we'll solve for this guy. Notice my concentration is getting 4 times less concentrated. That means my volume must increase 4 times. So let's see if that makes sense when you solve for x. 3 times 500 is 1500. divided by 12 equals 125. So ask yourself, did that proportion make sense? 125 milliliters. Okay, and of course this is V1. How much you start with? That's not what the question asks. How much water needs to be added? So 500 minus the 125 is 375 milliliters of water to add. If I want to add that amount to my 125, I'll have 500. Okay, next one, number 4. If a Na2SO4 solution is 0.5 molar, determine the following. Okay, so whenever this dissolves, it's Na2SO4 goes to 2 NAs and 1 SO4. All right, so in this situation, this initial concentration is 0.5. And this is a pretty straightforward question. We want to be able to look at the stoichiometric ratio. It's a 1 to 2 ratio. So this guy is going to be times 2, because there's 2 of them there, is 1 molar. The sulfate is a 1 to 1 ratio. It's 0.5. And the ions is 1 to 3 ratio times 3. So if I dissolve 10 sodium sulfates, how many ions do I get? I get 30. So times 3 is 1.5 moles per liter. Very important skill there. Okay, dilutions. We've done 2 dilutions already. So I'm not going to do any more dilutions here. Any questions, please let me know. This is audio workbook. Alright, so it says here, draw relative proportions of quantities of samples of ions A. Sample A include 2 water molecules. Alright, so just make this a little bit thinner line. Alright, so we have 0.2 molar Na3P. Okay, so as I mentioned, Na3P dissolves form 3 Na pluses plus 1 P negative 3. And I would just show this as Na plus, Na plus, Na plus, P minus 3. So just add some water molecules. So 2 water molecules. So I'd want to draw the water molecule probably like this. That's a partial negative by a positive. And I guess I could draw this one showing the hydrogen. And it doesn't say to draw any, label any forces or anything like that. So there we go. Write the dissolving equation for the salt. All right, did that above here. Check. All right. And then what's the concentration? All right, well, this guy is going to be times 3, which is 0.6. And this guy is a 1 to 1 ratio, just 0.2. 3 times more than this one, which is why we have 3 times the sodiums. 50 milliliters of sample A is added 200 milliliters of water. Okay, so it's a dilution formula. Now again, it starts out at 0.6 and 0.2. And all I'm doing is adding solvent, but I'm not taking the whole thing. So it's going to be molarity equal, let's do it this way. So there's a long way and a short way. Maybe I'll do the short way for the sodium. I'll do the long way for the phosphide. So the short way is just all we're doing is adding solvent. So it's a dilution. M1V1 equals M2V2. M1 is 0.6. Keep in mind where I got that. V1, it's only taking 50 milliliters of the sample. And it's going to add 200 milliliters of water, so my total volume is 250. My volume is increasing what appears to be 5 times. It should decrease in concentration 5 times. There we go, solve out. And 0.6 times 50 divided by 250 and 0.12. is that concentration. Okay. Now let's do the long way. Now the long way always works, and it's just using the molarity formula. Molarity equals moles per liter. I want my new moles divided by my new liters. Now the new moles happens to be the same as the old moles because nothing was added or changed, but that could be different. By mixing two solutions together, this would work nicely if I add up all the moles I have is divided by the new volume. So either way, now let's take a moment and do this. I have I'm going to use this formula twice. So 0.2 concentration of the phosphide. I got 50 milliliters, 0.05 liters. Solve for moles. Right, this is 1.2 is 1/5 of 0.05. So 1/5 of 5 is 1. So this is going to be equaling 0.01 moles. All right, 0.01 moles, and then I'm going to divide that by the new volume, which is 0.250 liters. All right, so we got 0.01 divided by 0.250, and we get 0.04. 0.04 moles per liter. Next. All right, we're getting more into stoichiometry, but this is definitely in this chapter. So I have a 100 milliliters sample of 0.5 molar solution of NaCl reacts with 0.25 molar solution of silver nitrate until no more silver chloride precipitates. Okay, so a couple things I notice about this reaction. One, it's a 1-to-1 ratio. Okay, this guy's forming a solid. This guy is just flowing around. Okay, a few things also I noticed. One, I have 0.5 molar of NaCl and 100 milliliters of NaCl. Okay, and then this guy's half as concentrated. So keep in mind, molarity times volume liters equals moles. And that's an important proportion to remember. If I double the volume, I double the moles. And or if I double my concentration, I double my moles. So in this situation, the proportional way of solving this question is that because I have half the concentration, I will need twice the volume to match it. So the answer is going to be 200 milliliters. 200 milliliters of this stuff is required to get the same quantity of moles as this stuff would. How would I actually calculate that? What if I didn't know that, or if the numbers weren't so nice? What I would do is solve this out. How many moles of this do I actually have? So I would go, molarity is 0.5 times a volume of 0.1 liters is 0.05 moles. And then I would say, okay, in the reaction, for every 1 NaCl, I require 1 AgNO3. Okay, so that's a stoichiometric ratio, 1-to-1 ratio of NaCl to AgNO3. And this means I need 0.05 moles of AgNO3. And then I would use the same formula, molarity times the volume equals the moles. And now, in this case, I want to solve for volume. So let's rework this thing. Let's do molarity equals moles per liter. I want to solve for liters. Things move diagonally, so it's going to be liters equals moles per molarity. Okay, so I just swap these two. Moles is 0.05. The molarity is 0.25. Okay, and in this case, divide out 0.05 divided by 0.25, and I get 0.2. And of course, 0.2 liters is equivalent to 200 milliliters. I could also have done an ice table where I have initial stoichiometric ratio end, showing that just ever so quickly. I'm going to use the net ion equation. Cl minus plus Ag plus yields AgCl. And I could write in the initial stoichiometric ratio end. I could solve it out. Just as this is a data table. This is the work to fill the data table in. All right, well, this is the net equation. So draw a picture. So in this case, if I mash them equally, I would have Na pluses floating around, I have NO3 negatives floating around, and the bottom, I would have AgCl. All right, you're always welcome to pause a video whenever you want to try a question out. When 30 milliliters of 0.1 molar NO3 is added to 30 milliliters of 0.1 molar NaCl, aqueous solution of sodium nitrate and solid AgCl is formed. How much solid AgCl is produced? Okay, so you can pause the video, take a look. All right, so the first thing I do is I have to wrap my brain around what this reaction looks like. All right, so pencil math is your friend. So AgNO3 plus NaCl yield AgCl plus NaNO3. And someone else might say, right to the chart is plus 1, minus 1. So it's going to be Ag plus Cl minus yields AgCl. So it's 1-to-1 ratio. That's important. All right, so now I have equal volumes. 30 milliliters, 30 milliliters, okay. 0.1 molar and 0.1 molar, okay. So they're both going to run out exactly the same time. So if I know how many moles of this guy I have, it equals the moles of this guy, and should equal the moles of this guy. So either one you want to do. So let's just find the moles of the silver nitrate. It's 0.1 equals X moles, 0.03 liters for moles, and the answer is 0.003 moles. And of course, they're catching you to see if you understand the idea of limiting reactant and running out of reaction. So straight up the alley of stoichiometry. All right, proportions. More of the same here. Okay, so now we have a reaction here. And is it balanced? I got one calcium. I got 2 oxygens, and I only have 1 here. So I'm going to have a 2 here. And then 4 hydrogens, and I have 2 here, and I'd like it to have a 2 right here. And that also completes my chlorines. Okay, so now it's balanced. 100 milliliter sample of 0.5 molar of this. So I got a concentration and a volume. Reaction with 100 milliliters of 0.5 molar HCl. Okay. What's the limiting reactant? Well, because we have equal volumes of equal concentrations, we have equal moles. That's a really important concept. Molarity times volume equals moles. That's just rearranged from the molarity formula. You should realize that if this is equal and this is equal, then this is equal. So, equal moles is what we're starting with, but this is used up twice as fast. Therefore, this is my limiting reactant. At this point, what is the concentration of each ion in the solution after the reaction? Okay, let's do this. I have calcium, I have hydroxide ions, I have H plus ions, I have chloride ions. All right, and in this case, before I get started here, what's my concentration before I get started? It's 0.5, 0.5. This is doubled, so let's change that to 1. 0.5 times 2 is 1. This is 0.5, and this is 0.5. This is the start. Okay. Now, I'm going to be doubling my volume. to 200 milliliters. The the calcium and the chloride have nothing to do with this reaction. This is forming a liquid, and this is just staying aqueous. So these guys aren't taking part in the reaction. So this guy and this guy just hang out, and because the volume's doubled, it drops to 0.25. And this is just proportions, trying to understand the proportions that we have here. Okay. Now, my limiting reactant would be the chloride ion, the hydrogen ion. It's going to be completely wiped out down to 0. That's my limiting reactant ion. And the hydroxide, it starts at 1, but I'm using half of it. I'm consuming half of it. That drops it down to 0.5. And I'm doubling my volume. It drops to 0.25. And that is what I have. Draw a picture. Okay, so if we were to draw out, I'm going to draw one loop of this thing. So I'm going to draw 2, 2, 1, 2. Okay, that will give me the whole thing. And the reason why I'm drawing 2 and 2 is because these things have equal moles. So I have to draw the same numbers. All right, so calcium plus 2, OH negative, OH negative, Ca plus 2, OH negative, OH negative. Okay. This guy, 2 of them, H plus, Cl minus, Cl minus. Okay. Now, like I said, the chlorides and the calciums do nothing. So, Ca plus 2, Ca plus 2, OH negative, OH negative. Sometimes I circle them as I draw them. This guy and this guy, this guy, and this guy are all consumed. Okay, now 1H can take out, well, I was supposed to draw 2 of these guys. I'm missing an H. There it is. Okay, very good. That's right. HCl, HCl. Okay, so one guy grabs onto, I should say, 2 H2O. So in this situation, an H and an OH can each cancel each other out. That's one water. I can just put it here, H2O. And this guy grabs onto this guy, meaning another H2O. And then, of course, we have an excess, 2 of these guys. Excess and excess. And this is going to be OH negative, OH negative. Hence that. Okay. NaOCl and HCl form chlorine gas. So we got a reaction here. Reaction 2 occurs when an excess 6 molar HCl, that's this guy, is added to 100 milliliters of this stuff of unknown concentration. If the reaction goes to completion and 0.01 moles of chlorine is produced, what was the molarity of the NaOCl solution? All right, so a bunch of stuff here. Let's start picking it apart. And you can pause this problem and try it. It's a nice stoichiometry problem here. All right, so we have molarity equals moles per liter out of this stuff right here. So my original, I want my original volume and I want my original moles to give me my original concentration. Okay, so my original volume, as stated right here, is 0.1 liters. So now I just want to know how many moles I had of this stuff. Well, this is not going to be needed. It's in excess. So all I'm really going to use is my chlorine. I know that for every one of these that get produced, I had one of these. And this is going to be removed entirely because it's a limiting reactant. If I know how many moles of this I got, then I know how many of those I had. And of course, one chlorine and one chlorine, those have to be the same coefficient. All right, so what do we got for those? It says 0.01 moles of chlorine. So I must have had 0.01 moles of this guy, and the answer, therefore, is 0.1. And this would be moles per liter. 0.01 divided by 0.1 is 0.1, and therefore C is my answer. go. And that's just pretty much it. Some nice calculations as well. Thank you very much.